there are arrivals that announce themselves with a banner across the sky, and others that move in almost invisibly, first as a flicker in radio noise, or a shift in a forecast, or a quiet message from a space weather center hours before most people notice anything at all. A solar storm belongs to that second kind. It begins far from us, in magnetic knots on the surface of the sun, and then crosses the distance between star and planet as radiation, particles, and moving clouds of plasma. By the time it reaches Earth, it can become many things at once: a curtain of aurora over unfamiliar latitudes, a disturbance in radio and navigation, a drag on satellites, a pressure on power systems, and a reminder that even here, under an atmosphere and a magnetic shield, we still live beside a star. Welcome in, I'm Madeline Rowe, and tonight we're opening the case file on solar storms. And if these quiet science case files help you settle in, subscribe, and there'll be another one waiting for you soon. Back in my office, a small desk lamp pulls warm light across a folder labelled Solar Storms. The window beside me holds a dark pane of sky, but it does not feel empty tonight. It feels like a boundary, one side calm and lamplit, the other side full of flowing fields and invisible weather. A loose page at the edge of the desk lifts now and then in the draft from the vent, just enough to remind me that motion does not have to be loud to matter. I rest my hand on the folder, ease it open, and let the first pages of tonight's case file on solar storms fall into the light. The first thing to do with a topic like this is to make it less blurry. Solar storm is a useful phrase, but it can also hide too much. It sounds like one event, one blast, one single thing the sun does. In practice, it is a chain. Sunspots and active regions build magnetic tension. A solar flare releases a burst of radiation. A solar radiation storm can hurl energetic particles outward at enormous speeds. A coronal mass ejection, or CME, can launch a huge cloud of magnetized plasma into space. Then, only if the timing and geometry are right, Earth responds with a geomagnetic storm. That last step matters. A geomagnetic storm is not the eruption at the sun. It is what happens here, in and around Earth, when the solar wind and Earth's magnetic environment begin trading energy fast enough and long enough to disturb the whole system. That distinction gives the whole case its shape. We are not really telling the story of a blast. We are telling the story of a connection. The sun is not only a bright sphere lighting the daytime sky, it is a star made of hot, electrically conducting plasma, and plasma carries magnetic fields along with it. That means the sun is constantly threading, stretching, and rethreading magnetism through its own atmosphere. Some of that motion is steady enough that we call it the solar wind, the continuous outflow of particles from the sun. Some of it is abrupt enough that we give it special names: flare, CME, radiation storm, blackout, geomagnetic storm. And all of it unfolds in a system that includes not just the sun, but the space between worlds and our own planet's magnetic cocoon as well. To understand why the sun does this, it helps to stop thinking of it as a giant burning object in the ordinary sense. The sun is not like a candle or a furnace. Its energy ultimately comes from nuclear fusion in the core, where hydrogen nuclei are combined into helium under enormous pressure and temperature. That energy does not race straight outward in a clean beam. It works its way through layers. In the radiative zone, it diffuses outward through countless interactions, taking an astonishingly long time to make progress. Higher up, in the convective zone, hot plasma rises, cools cools, and sinks again in great overturning motions. By the time the energy reaches the visible surface, it has already been part of a long interior journey. What we see as the sun's light is therefore only the outer expression of a much deeper engine. The sun also has layers that matter for space weather in a more direct way. The visible surface is called the photosphere. Above it lies the chromosphere, and above that the corona, the sun's outer atmosphere, which extends far into space and is the birthplace of the solar wind. One of the remarkable facts about the sun is that the corona is much hotter than the visible surface below it. This is one of the classic puzzles of solar physics, because we are used to heat fading with distance from a source, not intensifying again higher up. The leading explanations involve magnetic processes, waves, and the conversion of magnetic energy into thermal energy. That puzzle sits close to tonight's topic, because the corona is also where large magnetic structures form, twist, and sometimes erupt. Once you begin to picture the sun as a star with an interior engine, a convecting outer layer, a visible surface, and an extended magnetized atmosphere, solar storms begin to feel less like sudden tantrums and more like the natural consequences of a restless system. This is not a solid ball with a quiet shell. It is a churning plasma body, threaded with magnetic fields and layered with structures that can store and release energy. The story is not really about a calm object that occasionally misbehaves. The story is about a dynamic object whose ordinary state already contains motion, and whose more dramatic moments are simply the points at which hidden stresses become visible. A useful step here is to slow down over the word plasma. Plasma is sometimes called the fourth state of matter, but that phrase can feel like a classroom label unless you pause on what it means. A plasma is a gas in which many atoms have been ionized, so electrons and ions move somewhat independently. Because it contains charged particles, plasma responds strongly to electric and magnetic fields, and in turn, it can generate and carry those fields with it. This is why the sun cannot be understood as merely hot gas. The word gas does not capture the magnetic life of the material. Plasma does. And because the sun is made of plasma, magnetism is not a small surface detail. It is part of the architecture of the star. A steel ball can rotate as a unit. The sun cannot. Its equator rotates faster than its higher latitudes, and the material below the visible surface is also in motion. This pattern is called differential rotation, and it matters because it stretches magnetic field lines over time. Imagine drawing a set of stripes on a rubber sphere and then turning the middle faster than the top and bottom. Before long, the stripes would twist, shear, and distort. The sun does something like that, except the stripes are magnetic fields and the sphere is not solid. On top of that, convection is constantly dragging magnetic flux upward and downward. Over time, these processes help build the tangled magnetic structures associated with sunspots and active regions. A sunspot, despite the name, is not a hole. It is a cooler patch on the photosphere, where concentrated magnetic fields inhibit the normal upward flow of heat. Against the brighter surrounding surface, it looks dark, but isolated by itself, it would still be intensely bright. Sunspots matter not because they are shadows, but because they mark places where magnetic fields have become concentrated and complicated. They are the visible component of active regions, and active regions are where many eruptions begin. So a sunspot is less like a blemish and more like a note pinned to the sun saying, something magnetically interesting is happening here. Some sunspots appear alone and relatively simple. Others arrive in groups with shapes and magnetic arrangements that suggest greater complexity. Solar physicists classify active regions partly by magnetic structure, because regions with more intricate, tightly packed, oppositely directed fields tend to be more eruption-prone. You do not need to memorize the alphabet soup of magnetic classes to feel the underlying logic. Simpler arrangements are often calmer. More mixed and stressed arrangements are often more dangerous. The active region becomes, in effect, a place where the sun has been storing magnetic strain in a geometry that may not hold forever. This brings us naturally to the solar cycle. The sun's activity rises and falls over an approximately 11-year cycle, most visibly tracked by changes in the number of sunspots. During solar minimum, sunspots may be scarce and solar activity relatively subdued. During solar maximum, sunspots become more numerous, active regions multiply, and eruptions become more common. But the cycle is deeper than a count of spots. Over the course of about 11 years, the sun's global magnetic field evolves toward a reversal, and over roughly 22 years, the magnetic cycle completes a full return to its original orientation. In that sense, the familiar 11-year sunspot cycle is part of a longer magnetic rhythm. I find that useful because it prevents solar maximum from sounding like a sudden mood. It is a phase in an ongoing magnetic pattern. The sun is not waking up angry after a nap. It is passing through part of a cycle that repeatedly reorganizes its large-scale magnetism. During maximum, there are more active regions, more places where magnetic structures can become complex, and more chances for flares and coronal mass ejections. Earth is not guaranteed to be struck by anything dramatic. Space is far too large for that. But the odds of notable space weather rise because the source itself has become busier. There is a nice office metaphor hidden in that idea. A room may look the same at a glance. The same lamp, the same desk, the same walls. But if more people are moving through it, more folders are open, more phones are ringing, and more small tasks are leaning against one another, then the character of the room changes. Nothing essential has changed, and yet everything is more likely to spill into something else. Solar maximum is a little like that. The sun is still the sun, the light is still the light, but the traffic of magnetic possibility becomes denser. When those magnetic structures become sufficiently stressed, one of the key processes that can occur is magnetic reconnection. The phrase sounds technical, but the central picture is manageable. Magnetic field lines are a way physicists describe the direction and structure of a field. In plasma, where charged particles and magnetic fields are intertwined, those field lines can be distorted and forced together. Under the right conditions, regions of opposing magnetic orientation can rearrange into a new topology. When they do, stored magnetic energy can be converted into heat, radiation, and particle acceleration. Reconnection is one of the ways the sun turns quiet magnetic stress into observable event. This is the point where many descriptions rush ahead into spectacle, but it is worth slowing the scene down. Reconnection is not fireworks in the ordinary sense. It is a change in structure. If you have ever seen a stack of papers bend and slip into a new position all at once after building strain for too long, or a knot in a cord suddenly give way and transform the shape of the whole line, you have a faint analogue. The action looks sudden because the stress had been accumulating quietly. Solar eruptions are often like that. The visible drama is the final release of a longer magnetic preparation. Now we can separate the first major phenomenon in the storm chain, the solar flare. A flare is fundamentally a burst of electromagnetic radiation emitted across multiple wavelengths. X-rays, extreme ultraviolet, visible light, radio waves, flares are broad-spectrum events. This matters because radiation travels very fast, so when a flare happens, the first effects at Earth can arrive almost immediately in astronomical terms. A flare is not a blob of solar material physically colliding with us. It is an abrupt brightening and release of radiant energy. Flares are classified by their peak X-ray brightness. At the stronger end are X-class flares, then M-class, then C-class, and smaller categories beyond that. The scale is logarithmic, so each step represents a substantial difference in intensity. This is helpful because it reminds us that a flare is not one fixed size of event. It is a family of events across a wide range of strengths. A moderate flare and a major X-class flare are not separated by a minor stylistic difference. They are physically different in scale. One direct consequence of strong flare radiation is the radio blackout. When X-rays and extreme ultraviolet radiation from a flare reach Earth, they can increase ionization in the sunlit side of the upper atmosphere, especially the ionosphere's lower regions. That changes how high-frequency radio waves propagate. In some cases, signals are absorbed more strongly, and long-distance HF communication is degraded or lost. This is why solar flares can have operational effects even before any slower-moving plasma cloud arrives. The disturbance begins not with impact in the ordinary mechanical sense, but with radiation altering the electrical behavior of the atmosphere. That leads to one of the simplest but most important distinctions in the whole episode. The sun can trouble Earth in more than one way, and on more than one schedule. A flare can disrupt radio communication through radiation. A solar radiation storm can deliver energetic particles. A coronal mass ejection can send a cloud of plasma and magnetic field outward over many hours or days. A geomagnetic storm is Earth's magnetic response to an encounter with solar wind structures. If you collapse all of these into one dramatic sentence, something like the sun exploded and the storm hit, you lose the fine structure of the science. Tonight, it is worth keeping the pieces visible. The next piece is the solar radiation storm, sometimes discussed under the broader topic of solar energetic particles. These are not just photons from a flare, but actual charged particles, especially protons, that have been accelerated to very high energies by solar eruptions. They may be accelerated near the flare site, near shock fronts driven by coronal mass ejections, or through a combination of processes. The details can become intricate, but the practical point is clear. Very energetic particles can arrive far faster than a CME and can pose distinct risks to spacecraft, astronauts, and aviation, especially on polar routes where Earth's magnetic shielding is less protective. This is one of the reasons space weather is not only about pretty aurora or about some distant curiosity in solar astronomy. It is also about exposure, electronics, and operations. A spacecraft beyond the densest shielding of Earth's atmosphere does not get to ignore an incoming particle storm. Neither does a crewed mission traveling outside low Earth orbit. Even in ordinary commercial aviation, intense solar particle events can matter because polar flights depend on radio communication and operate in a radiation environment different from that at ground level. Then comes the coronal mass ejection, the phenomenon that most resembles a moving weather system in the popular imagination. A CME is an enormous eruption of plasma and embedded magnetic field from the sun's corona. These events can carry billions of tons of material outward into the heliosphere. In imagery from solar observatories, they often appear as vast bubbles, loops, or halos expanding away from the sun. A CME is not simply a puff of gas. It is a magnetized structure, often thought of in terms of flux ropes and large-scale field organization, moving through an already magnetized solar wind. This distinction between flare and CME is worth dwelling on because the two are so often spoken as though one automatically includes the other. Sometimes a strong flare is associated with a CME. Sometimes the relationship is looser. Sometimes a CME can occur with less dramatic flare signatures than a casual observer might expect. The Sun does not always arrange its major events for neat narration. The two phenomena often travel together in public language because both come from active regions and eruptions, but physically they are different things. The travel time of a CME introduces another rhythm into the case. Instead of near immediate radiative effects, there is anticipation. Depending on speed, a CME may take roughly 1 to several days to reach Earth, though the most extreme can arrive faster. During that interval, forecasters watch and refine. Models estimate propagation. Spacecraft monitor solar wind conditions farther upstream. Operators pay closer attention. It is one of the only kinds of weather in which the storm can begin with a flash at the source, continue with a long invisible crossing, and culminate in a magnetic encounter long after the first headlines have faded. The space between Sun and Earth is not empty in the way an unused room is empty. It is filled with the solar wind, the continuous outward flow of plasma from the corona. That outflow is not perfectly smooth. It has slow streams, fast streams, shocks, sector boundaries, and magnetic structures embedded within it. The Sun's rotation also shapes the heliospheric magnetic field into a spiral pattern, often called the Parker spiral, because the solar wind streams outward while the Sun continues turning beneath it. So when a CME travels toward Earth, it is not moving through a blank vacuum. It is moving through an already active medium, one whose background conditions can influence how the event evolves. There are also solar disturbances that are less famous than large CMEs, but still important. Coronal holes, regions where magnetic field lines open more directly into space, can be sources of high-speed solar wind streams. When those high-speed streams interact with slower solar wind ahead of them, they can form compression regions and drive recurrent geomagnetic activity at Earth. These storms are often less dramatic than the most extreme CME-driven events, but they remind us that space weather is not one mechanism only. The Sun can stir Earth's magnetic environment through repeated streams as well as one-off eruptions. By now, the case file has built a sequence from source to journey, and we can finally turn more fully toward Earth. A geomagnetic storm does not happen simply because something large leaves the Sun. It happens because Earth's magnetic field and the incoming solar wind begin interacting in a particularly effective way. The key issue is magnetic orientation. If the interplanetary magnetic field carried by the solar wind, or CME, points southward when it reaches Earth's dayside magnetosphere, it is more favourably oriented for reconnection with Earth's field there. That opens a pathway for efficient energy transfer into the magnetosphere. This is one of the most elegant points in the whole story. Storm intensity is not just about size or speed, it is also about alignment. A large CME with an unhelpful magnetic orientation may produce less disturbance than feared. A well-oriented magnetic structure can be surprisingly effective. The encounter is therefore partly a question of geometry. The Sun sends out a magnetized cloud, and Earth's magnetic shield asks a quiet question of it. How are you pointed? Earth's magnetosphere is the large magnetic cavity carved into the solar wind by our planet's own field. On the sunward side, it is compressed by the pressure of the solar wind. On the night side, it stretches far away into a long magnetotail. Ahead of it sits the bow shock, where the supersonic solar wind is slowed and diverted, and just inside that lies the magnetosheath, a turbulent region of shocked solar wind plasma. The boundary itself is the magnetopause. All of these structures matter because a geomagnetic storm is not an event occurring in empty space around Earth. It unfolds through this layered architecture. In quiet conditions, the magnetosphere does a remarkable amount of shielding. It redirects most solar wind plasma and protects the atmosphere from direct, continuous erosion. But shield does not mean wall. The magnetosphere is dynamic, elastic, and responsive. It shifts with changing solar wind pressure. It stores energy in its stretched tail. It supports large current systems. During storms, these properties become more pronounced. The whole structure becomes more energized and more variable. On the day side, southward solar wind magnetic fields can reconnect with Earth's field, allowing solar wind energy to enter the magnetosphere more directly. That energy is then carried into the magnetotail, where further reconnection can occur. In broad terms, the tail stores magnetic energy and then releases some of it, accelerating particles and driving flows back toward Earth. This process helps power auroral activity and other disturbances. It is one reason the aurora is not just an atmospheric light show, but part of a much larger magnetic circulation. At this point, it helps to distinguish between a geomagnetic storm and an auroral substorm. The two are related, but they are not the same thing. A geomagnetic storm is a larger scale disturbance of Earth's magnetic environment, often associated with sustained solar wind driving and the intensification of the ring current. An auroral substorm is a shorter-lived explosive release of energy in the magnetotail, often producing sudden brightenings and expansions of the aurora. During a major geomagnetic storm, multiple substorms may occur. This is another example of why solar storm language benefits from patience. One event can contain smaller events nested inside it. The ring current deserves a quiet moment because it shows how the invisible becomes measurable. The ring current is a circulating population of energetic charged particles trapped around Earth. During storms, it can intensify, and as it does, it slightly weakens the magnetic field measured at Earth's surface. This is one reason storm indices change. A storm is not only something seen in the sky, it is also something written into magnetometer traces and numerical indices by the behavior of particle populations around the planet. Then there are the auroral electrojets, powerful electric currents flowing through the high-latitude ionosphere. These currents are closely connected to auroral activity and to the broader electrodynamics of geospace. If the ring current speaks to global magnetic disturbance, the electrojets speak to the intense high-latitude current systems that accompany the visible aurora. Together, they help explain why a solar storm can be felt simultaneously by instruments on the ground, satellites in orbit, and human observers looking up from snowy roadsides or quiet neighborhoods. Scientists summarize some of this disturbance with indices like K, P, and DST. K is a planetary geomagnetic activity index built from magnetometer observations at multiple sites. DST is closely related to the ring current and tracks the depression of the horizontal component of Earth's magnetic field during storms. These numbers are not the storm itself, but they are useful fingerprints. They give a common language to forecasters, grid operators, researchers, and mission planners. A line on a graph may not look dramatic, but sometimes it is the cleanest possible description of an invisible system having a very consequential day. Operational space weather also uses named scales, which are worth pausing on because they tidy up the case beautifully. There are radio blackout scales for flare-driven disturbances to the ionosphere. There are solar radiation storm scales for energetic particle events. And there are geomagnetic storm scales for magnetic disturbance at Earth. These are sometimes labelled R, S, and G. That simple separation does a lot of work. It reminds us that not every space weather problem belongs to the same physical category. One event may produce all three in sequence, but the categories remain distinct because the mechanisms and impacts are distinct. At the high end of the geomagnetic scale lies G5, the extreme category. It is the sort of label that naturally attracts headlines, but behind the drama sits a practical point. These scales were built to communicate real-world consequences: voltage control problems in power systems, increased satellite drag, spacecraft charging, degraded navigation, and aurora at unusually low latitudes. They are not poetic rankings. They are operational shorthand for how much the space environment is leaning on the technologies below. To follow those consequences, we need to talk about the ionosphere and the thermosphere, the upper atmospheric regions where much of space weather's terrestrial expression becomes tangible. The ionosphere is the part of the upper atmosphere containing enough free electrons and ions to affect radio propagation. The thermosphere lies in overlapping altitude ranges and responds strongly to solar heating. During quiet conditions, these regions are already dynamic. They change with sunlight, latitude, season, and local time. During solar storms, they become more disturbed, more structured, and more difficult to treat as a stable transmission medium. This matters because many modern systems depend, often invisibly, on the upper atmosphere behaving within familiar bounds. High-frequency radio communication depends on reflection and refraction through ionized layers. Satellite navigation signals pass through that same region and can be delayed or distorted by changes in electron density. The thermosphere's density determines drag on satellites in low Earth orbit. So when a solar storm heats and expands the upper atmosphere or rearranges the ionosphere's electron content, it is not just making academic noise in a rarefied region. It is altering a working interface on which real systems rely. One elegant example is global navigation satellite systems. When people think of satellite navigation, they often picture a clean path between a satellite and a receiver. But the signal must pass through the ionosphere, and the ionosphere is electrically active. Disturbances there can delay the signal and introduce positioning errors. During stronger geomagnetic activity, irregularities can produce rapid fluctuations known as scintillation, causing signal degradation. So even before you begin worrying about the health of the satellite itself, the path between sky and ground may already have grown more difficult. Satellite drag is another good example of how subtle physics becomes practical engineering. During geomagnetic storms, energy input into the upper atmosphere heats it and causes it to expand. The atmosphere does not stop at a neat edge. It thins gradually with altitude. When it expands, the density at a given low orbit altitude can increase. Satellites that normally move through very tenuous air suddenly feel more resistance. Over time, that changes their orbits, which means operators may need to recalculate tracking and perform more adjustments. In a world with many thousands of satellites, even modest changes in drag conditions can become an issue of coordination and safety. Spacecraft charging adds yet another layer. Energetic particles and disturbed plasma environments can deposit charge on spacecraft surfaces or influence internal charging in electronics. These effects can lead to anomalies, temporary upsets, or in worse cases, damage. Again, the storm is not throwing lightning bolts directly at a satellite in the cartoon sense. It is altering the charged particle environment around the spacecraft, and spacecraft are electrical systems living inside that environment. For astronauts, especially beyond the deepest shelter of Earth's magnetic field, solar energetic particle events deserve particular respect. Low Earth orbit still benefits from some shielding by Earth's magnetic field and the spacecraft itself, but missions to the Moon or beyond do not enjoy the same protective context. A major solar particle event is therefore not just a forecasting problem, it is a human exposure problem. Sheltering strategies, mission planning, and monitoring all become part of the broader space weather story. This is one reason the study of solar storms is inseparable from the future of human exploration. Back on Earth, one of the most familiar and beloved consequences of geomagnetic disturbance is the aurora. Charged particles guided by magnetic field lines enter the upper atmosphere near high latitudes and collide with atoms and molecules there. Those atoms and molecules are excited into higher energy states and then emit light as they relax. Oxygen often gives the well-known green glow and, at higher altitudes, red. Nitrogen contributes blue, purple, and pink tones. The exact colours depend on species, altitude, and the energies involved. The visual forms of aurora are equally expressive. Arcs, rays, curtains, coronas, these are not cloud types in the meteorological sense, but luminous traces of magnetic geometry and particle precipitation. The aurora often forms in an oval around the geomagnetic poles. As geomagnetic activity intensifies, that oval expands toward lower latitudes. During major storms, people far from the usual auroral zone may suddenly find the northern or southern sky glowing. This can make a solar storm feel like a gift to casual observers, but the beauty is inseparable from the electrodynamic disturbance that produced it. Aurora also has a quality that fits this channel especially well. It is dramatic without being loud. It is evidence without impact in the ordinary tactile sense. A tornado announces itself to the body through sound, pressure, and immediate danger. Aurora announces itself to the eye as a kind of magnetic handwriting. That can make it easy to forget how much machinery lies behind it. Every green arc is the visible edge of a much larger conversation among the solar wind, the magnetosphere, and the atmosphere. It is worth saying clearly that space weather can produce beauty and operational stress at the same time. The same storm that sends families outside to stare at a crimson horizon can also complicate aviation routes, degrade radio service, or force satellite operators into a more careful posture. Beauty here is not evidence of harmlessness, nor is it evidence of disaster. It is evidence that an invisible energy transfer process has reached the point of visible expression. That broader process can also reach the ground in less poetic ways. Geomagnetically induced currents arise because changing magnetic fields can induce electric fields in the ground and in long conductors. Modern power grids, with their extensive transmission lines and grounded transformers, are one place where those induced currents can become operationally significant. The risk depends on storm strength, regional ground conductivity, grid design, and other factors, but the principle is beautifully simple. A disturbance in space changes magnetic fields over Earth, and those changing fields induce electrical effects in infrastructure built on the ground. Pipelines can also feel the influence. Long conductive systems buried in the Earth may experience changes in corrosion-related potentials during geomagnetic disturbance. This is not the most famous space weather effect, but it is a useful reminder that our technological relationship with the planet is electrical in more ways than one. The storm need not strike an antenna or a spacecraft directly to matter. It can lean on the distributed conductive skeleton of our civilization through the ground itself. To see how all of this has played out historically, the case file turns first to the Carrington Event of 1859. This is the benchmark storm, the one that nearly every public discussion mentions, and for good reason. Observers recorded extraordinary auroras at unusually low latitudes. Telegraph systems behaved in startling ways, including shocks to operators and strange continued function even when disconnected from power. What makes Carrington so important is not just its intensity, but the fact that it occurred in a partially electrified world. It gives us a glimpse of an extreme solar storm before the age of satellites, dense electronic networks, and globally synchronized infrastructure. There is something almost eerie about reading 19th century descriptions of a space weather event. The language belongs to a world without plasma physics or orbital asset management, and yet the witnesses are clearly describing the same Sun-Earth connection we study today. Telegraph wires sparked, skies glowed, people far from polar regions looked upward in confusion and awe. Carrington reminds us that the physics came first. Our terminology came later. The sun was capable of this before we knew what to call it. The March 1989 storm offers a different kind of lesson. By then, the world was much more dependent on large electrical networks, and the storm's contribution to the Hydro-Québec blackout turned space weather from an upper atmosphere curiosity into an infrastructure concern for the public imagination. Here, the story is not mainly one of spectacle in the sky, though there was that too. It is a story about coupling, magnetic disturbance above, induced currents below, and the vulnerability of interconnected systems in between. The event became part of the reason utilities, agencies, and researchers took geomagnetic risk more seriously. The Halloween storms of 2003 expanded the modern lesson further. These were not isolated as a single moment, so much as a cluster of intense solar activity that lit the skies and challenged technological systems in the satellite era. By the early 21st century, our dependence on space-based assets was far greater than in 1989, and so the relevance of severe space weather had broadened. The Halloween storms became a vivid reminder that solar activity can still push itself into contemporary life in ways both beautiful and disruptive. Then there is the July 2012 near miss, a case that fascinates scientists and public audiences alike because it teaches through geometry. A powerful eruption crossed Earth's orbital path after Earth had already moved past the point of intersection. In simple terms, the storm missed because Earth was not there. That may sound almost anticlimactic, but it is actually one of the most revealing facts in the whole field. The sun does not tailor eruptions for our benefit or our fear. It launches them into space, and whether they matter to us depends partly on alignment. A near miss like 2012 is therefore not just a what-if story. It is a reminder that extreme eruptions remain part of the sun's repertoire. This returns us naturally to May 2024, which works so well as a central case because it belongs entirely to the present. During that period, large active regions on the Sun launched multiple flares and coronal mass ejections. The result at Earth was the strongest geomagnetic storm in 2 decades, with Aurora seen at unusually low latitudes and the full modern machinery of space weather awareness. Forecasts, alerts, data streams, public photographs, operational monitoring engaged at once. Unlike Carrington, May 2024 is something people remember from their own phones and skies. What makes May 2024 especially useful is that it allows us to practice disciplined language. There were flares. There were likely radio blackout consequences on the sunlit side of Earth. There were CMEs crossing interplanetary space. There were magnetic conditions at Earth that made a strong geomagnetic response possible. There were auroras, there were technological considerations. If all of that is compressed into a single, vague phrase, the chain disappears. But if you keep the pieces distinct, the elegance of the science emerges. The event was not one thing, it was a sequence of related things, each with its own mechanism. That same discipline helps when discussing forecasting. Forecasting solar storms is not like forecasting a local rain shower, though there are similarities in spirit. Scientists monitor the sun with spacecraft that image the photosphere, chromosphere, and corona, with coronagraphs that reveal faint eruptions leaving the sun, and with solar wind, monitors stationed upstream of Earth. They assess active regions, flare probabilities, CME speeds, and likely arrival windows. But one of the hardest ingredients to know in advance is the magnetic orientation of an incoming CME. That crucial feature often remains uncertain until the structure is relatively close. This is part of why forecasts may become more confident as an event approaches. At the Sun, an eruption can be seen clearly enough. In transit, models can estimate timing and speed. Then, when upstream spacecraft sample the solar wind and magnetic field directly before it reaches Earth, forecasters gain more concrete information about what is actually arriving. The lead time there may be on the order of tens of minutes to an hour, which is invaluable operationally, but still not the same as knowing everything days in advance. There is a whole choreography of observatories behind this. Solar telescopes watch sunspots and active regions. Spacecraft like the Solar Dynamics Observatory image the sun in multiple wavelengths. Coronagraphs on missions like SOHO and others reveal expanding CMEs. Parker Solar Probe and Solar Orbiter are helping us understand the sun and inner heliosphere more intimately than before. Closer to Earth, spacecraft monitor the solar wind directly. Ground-based magnetometers track Earth's response. Radio instruments watch the ionosphere. When a solar storm happens, it is not observed from one place only. It is followed through a distributed web of instruments, each watching a different link in the chain. That network of watching is one of the quiet beauties of modern heliophysics. It means that a storm is never just an event at the Sun or just an effect at Earth. It becomes a traced process. We can see where active regions formed. We can watch a flare brighten. We can see a CME expand. We can model its path. We can measure the solar wind upstream. We can observe magnetospheric response. We can record aurora and ionospheric irregularities and changes in satellite drag. The whole event becomes a conversation among instruments, some on the ground, some orbiting Earth, some much farther away. And still there are uncertainties. That is not a sign of failure. It is a sign that we are studying a coupled plasma system with many moving parts. Solar eruptions evolve as they propagate. Their internal magnetic structure can rotate or interact with the background wind. Earth's response depends not only on the incoming driver, but also on pre-existing conditions in the magnetosphere and ionosphere. Even the same level of external forcing can produce somewhat different practical outcomes, depending on local time, latitude, infrastructure, and system readiness. A storm is not a single hammer blow on a featureless surface. It is an encounter between structured systems. I find the uncertainty strangely calming because it makes the subject feel more real. Perfect predictability belongs to toy systems and simple stories. The Sun-Earth system is neither. It is rich, layered, and occasionally surprising. There is always one more boundary, one more current system, one more scale of interaction to consider. That is not a reason to become alarmed. It is a reason to become precise. Precision also helps when thinking about preparedness. Space weather forecasting exists so that operators can make decisions in advance or in response. satellite operators may adjust posture. Power grid managers may increase awareness of geomagnetically induced current risk. Aviation routes may be reconsidered, especially for communication and radiation reasons. Scientists may focus observations on a developing event. The public may simply step outside to look for aurora. Preparedness in this context does not mean fear. It means behaving like a civilization that knows it lives under a star. There is also value in comparing Earth to other planets, if only briefly. Earth is not the only world with space weather, but it is unusual in having a strong global magnetic field and a dense atmosphere that together shape how solar disturbances are experienced. Mars, with its weak patchwork crustal magnetism and thin atmosphere, faces the solar wind differently. Venus, lacking an Earth-like internal global magnetic field, develops a different interaction altogether through its induced magnetosphere. Jupiter has a vast and powerful magnetosphere of its own, driven not only by the solar wind, but also by internal processes and material from its moon, Io. Seeing these differences helps make Earth's case feel less inevitable. Our particular version of space weather belongs to our planet's particular magnetic and atmospheric design. That comparison also helps answer a quiet question that sits underneath tonight's whole case file. Why does Earth get aurora, radio disruption, satellite drag, and geomagnetically induced currents, rather than simply being stripped bare by the solar wind? The answer is not that Earth is untouched. The answer is that Earth meets the solar wind with a specific kind of defense, a magnetosphere large enough to stand off much of the flow, and an atmosphere deep enough to absorb and transform incoming energy in layered ways. Mars shows what a weaker magnetic situation can look like. Venus shows what an induced obstacle can do without an Earth-like internal dipole. Earth, by contrast, is a world where the magnetic boundary and the upper atmosphere cooperate. The result is not immunity, but a particular style of interaction. And that is worth lingering over, because it means space weather is not only a story about the sun, it is also a story about the kind of planet we happen to live on. The same eruption leaving the sun is not experienced identically by every world. A magnetosphere changes the terms of the meeting. An atmosphere changes them again. A technological civilization changes them yet again. Space weather is always local in that sense. The star provides the disturbance, but the planet determines the character of the reply. That reply begins even before the most dramatic moments of a storm. In quiet times, Earth's magnetic environment is already alive with circulating particles, electric fields, shifting boundaries, and a constant exchange with the solar wind. Storms are not the beginning of activity. They are intensifications of a system that never fully rests. This is one reason the language of impact can be slightly misleading. It makes space weather sound as though nothing is happening, and then suddenly something strikes. In truth, there is always an ongoing relationship between Earth and the sun. Storms are episodes in that relationship when the coupling becomes especially effective, and the consequences become easier to notice. A good way to feel this is to imagine the magnetosphere not as a castle wall, but as a coastline. Coastlines are always meeting the sea. Waves are always arriving. The exact shape of the boundary changes with weather, tides, and long-term forces. Most days, the meeting is unremarkable. During a storm, the same coast can experience a very different exchange. The magnetosphere is similar. Its boundaries shift inward and outward with solar wind pressure. Its tail stretches and relaxes. Its currents strengthen and weaken. The solar wind does not have to wait for a rare appointment. It is always there, pressing, flowing, and offering the possibility of stronger exchange if conditions align. This is also why the sheath region ahead of a coronal mass ejection matters so much. When a fast CME ploughs through the slower solar wind ahead of it, it can drive a shock, and between that shock and the leading edge of the magnetic cloud lies a compressed, turbulent region known as the sheath. In some storms, the sheath itself can be highly geoaffective. It can contain strong, fluctuating magnetic fields and dynamic pressure changes that buffet the magnetosphere before the core of the CME even arrives. That means the storm timeline is sometimes layered even within a single event. First, the shock, then a compressed region of disturbed solar wind, then the more organized magnetic structure behind it. Each piece can matter. The shock arrival is often one of the clearest moments in solar wind data. Upstream monitors may show an abrupt jump in solar wind speed, density, temperature, and magnetic field strength. On the ground, magnetometers may register a sudden impulse as Earth's dayside magnetosphere is compressed. This does not yet tell you how strong the storm will become, but it does announce that the solar wind has changed state. It is a little like hearing the first hard rain hit the roof before you know whether the river will flood. The transition is unmistakable. The consequences still have to unfold. Then comes the harder part of the forecast, reading the magnetic field inside the disturbed flow. A strong southward component can open the door to efficient coupling. A northward one may keep the geomagnetic response relatively restrained. In this sense, forecasters are often waiting for orientation as much as for arrival. The CME can be large, fast, and impressive, but the question that matters for Earth remains quietly specific. How is the field pointed? It is one of the most beautiful examples in science of a dramatic event being governed by a geometrical subtlety. Even after the first coupling begins, a geomagnetic storm has structure. There is often an initial phase associated with sudden compression, then a main phase as the ring current intensifies and geomagnetic disturbance deepens, and then a recovery phase that can last much longer as the system gradually relaxes. This is useful to picture because it keeps a storm from sounding like a single peak on a graph. A storm has a rise, a depth, and an aftermath. Some effects happen early, some build over hours, some linger after the most photogenic aurora has faded. The recovery phase is especially easy to overlook because it is less theatrical, yet from a systems perspective, it matters. The upper atmosphere may remain heated. Satellite drag can stay elevated. Particle populations may continue adjusting. The magnetosphere does not snap back to perfect quiet the moment the strongest driving ends. It settles, redistributes, and works its way toward a less disturbed state. Many natural systems behave this way, and space weather is no exception. The system remembers the storm for a while. That memory can also show up in how one event prepares the stage for another. During active periods, multiple CMEs can leave the Sun in close succession. When that happens, later eruptions may travel through solar wind already modified by earlier ones. They may catch up, interact, or arrive in a sequence that sustains geomagnetic activity longer than a single isolated event would. This is one reason some historical storm periods are remembered as clusters, rather than as solitary moments. The Sun can produce episodes, not just individual acts. A sequence like that has an almost narrative quality to it, though the physics is doing all the work. One eruption clears a path, another follows into altered conditions. Shocks strengthen or merge. Magnetic structures interact. Forecasting becomes more difficult because the background is no longer quiet. The storm stops being one moving object and becomes a procession. For listeners, This may be one of the easiest ways to understand why some famous solar storm periods lasted for days and felt from the ground like a whole unsettled chapter rather than a single dramatic instant. That long chapter feeling also belongs to the ionosphere. The ionosphere is not one simple shell, but a set of regions whose ionization changes with sunlight, altitude, chemistry, and geomagnetic forcing. During the day, solar radiation creates and maintains ionization. At night, some layers weaken considerably. Storm-time electric fields and particle precipitation can rearrange that structure, especially at high and low latitudes. The result can be patches, gradients, and irregularities that make radio propagation more difficult to predict. To a scientist looking at data, the upper atmosphere during a storm can resemble a surface covered not in smooth paint, but in ripples, pockets, and moving scars. This matters a great deal for communications, because radio propagation is always part physics and part path. A signal is not just sent, it travels through a medium with its own state. Under disturbed conditions, the medium stops behaving like the clean background your system hoped for. Some frequencies that would normally carry well may be absorbed. Others may scatter strangely. A route that looked reliable at one moment may degrade at the next. This can be especially important at high latitudes, where auroral absorption and geomagnetic disturbance are more pronounced. It is one of the quieter truths of the modern world that much of our sophistication still depends on delicate, invisible paths. We think of advanced systems as solid and exact, but many of them rely on timing signals, radio links, propagation models, and physical layers of the atmosphere that are not under our control. Space weather exposes that dependency. It reveals that modern precision often rests on environmental assumptions. Change the environment, and the precision has to work harder. This is especially vivid in the world of satellite navigation. A navigation receiver may treat the incoming signal as a clock mark from space, but the path the signal follows is not perfect. The ionosphere delays it in ways that can often be modelled or corrected under ordinary conditions. During disturbed periods, however, those delays become less uniform. Small-scale irregularities can cause scintillation, rapid phase and amplitude, changes that make tracking more difficult. When enough of those effects accumulate, accuracy suffers. A farmer guiding equipment, an aircraft navigating, a surveyor measuring, a timing network synchronizing systems. Each may feel the same physics in a very different practical form. Aviation provides another beautiful example of how many layers a solar storm can touch at once. High-latitude flights are especially relevant because polar routes often rely on HF radio communication, where satellite coverage or other factors make that useful, and because magnetic shielding is weaker near the poles for energetic particles. During disturbed periods, airlines may weigh communication reliability, radiation considerations, and operational flexibility all together. The passengers on such a flight may experience nothing more dramatic than a reroute or a different message from the crew. Yet behind that calm is a chain of heliophysics, atmospheric science, and risk management running all the way back to a magnetic region on the sun. This is part of what makes solar storms such a satisfying topic for the channel. They link cosmic scale to ordinary consequence without losing scientific precision. A flare on the sun becomes, through a long chain of coupled systems, a question about whether a route over the pole is convenient today. A CME crossing interplanetary space becomes a concern about satellite drag and conjunction analysis. An auroral display over a quiet town becomes evidence of ring currents, electrojets, and magnetic reconnection. The scale changes are enormous, but the chain holds together. The same is true for spacecraft operations. Low Earth orbit is often spoken of as though it were cleanly separate from the atmosphere, but it is better understood as the upper fringe of a planetary environment. Satellites there move through a medium that is usually thin but never irrelevant. When the thermosphere expands during geomagnetic storms, orbital predictions become less certain, and drag-sensitive spacecraft feel the change first. That may sound like a narrow technical issue, yet in a crowded orbital regime, even small uncertainties can multiply into larger operational problems. A storm need not destroy anything outright to complicate the work of keeping track of what is where. There is also a philosophical lesson hidden there. We tend to imagine progress as insulation, as if better technology steadily removes us from nature. Space weather suggests something subtler. Sometimes greater technological reach means greater environmental sensitivity. The more precisely you depend on signals, timing, and orbit maintenance, the more you care about the condition of the upper atmosphere and near-Earth space. In that sense, sophistication does not abolish the environment. It creates new forms of dependence on it. The Moon offers a particularly sharp contrast. A person on Earth under a geomagnetic storm still has a magnetic shield and a deep atmosphere above them. A person on the lunar surface would not. A crewed mission in cislunar space would be watching solar weather with a very different kind of attention. This is one reason the study of solar storms belongs not only to Earth science and not only to solar physics, but to the future of exploration. The farther human activity extends beyond low Earth orbit, the more directly the Sun's variability becomes part of mission design, shelter strategy, and daily operational awareness. There is something almost poetic about that. For many generations, the Sun was the dependable light by day, and the object around which the calendar turned. Then it became, scientifically, a star among stars, though one close enough to study in exquisite detail. Now, as humanity extends activity farther from Earth, the Sun becomes something even more intimate, a local environmental factor for human travel. Space weather is the bridge between those ideas. It makes the Sun both astronomical and practical at the same time. Even here on Earth, the practical side does not diminish the wonder. In fact, it sharpens it. An aurora is lovelier, not less lovely, when you understand that it is the visible trace of charged particles guided along magnetic field lines into an excited atmosphere. A storm forecast is more interesting, not less, when you know it represents a chain of observations reaching from solar telescopes to upstream monitors to ground magnetometers. Science rarely makes beauty smaller. Usually it gives beauty more depth. That depth is especially apparent when we think about time. The light leaving the Sun takes only minutes to reach Earth. Energetic particles may arrive on the scale of tens of minutes to hours. A CME may take days. The magnetic response of Earth unfolds over hours and then recovers over longer intervals. Historical memory stretches the timescale farther still, from Carrington to Québec, to Halloween 2003 to May 2024. Human planning extends it again into the future, toward more satellites, more dependence on precise navigation, and more journeys beyond low Earth orbit. Solar storms are therefore not confined to one timescale. They link the immediate, the operational, the historical, and the civilizational. It is rare for a topic to hold all of those scales without becoming vague. Solar storms do because the causal chain is so strong. The Sun's magnetic complexity grows. Reconnection releases energy. Radiation, particles, and plasma move outward. Earth's magnetic and atmospheric systems respond. human systems notice. Once you have that structure in mind, details can accumulate without dissolving the whole. You can add Parker spiral, sheath field, ring current, thermospheric expansion, GPS scintillation, or transformer stress, and each still belongs to the same case file. There is also comfort in realizing that most days this entire system is present without becoming severe. The sun is always sending the solar wind. Earth is always standing in it. The magnetosphere is always doing its work. Not every active region produces a great storm. Not every CME is Earth-directed. Not every southward field remains southward long enough to matter strongly. Space weather is part of the background condition of living in the heliosphere, and extreme events are the upper end of a continuous distribution, not interruptions from a different universe. That continuity is important because it keeps the subject from tipping into melodrama. The sun is not either quiet or catastrophic. Earth is not either safe or doomed. There is a spectrum of activity, a spectrum of response, and a spectrum of consequence. Much of science becomes more accurate and more calming when it replaces binaries with gradients. Solar storms are a perfect example. A G1 storm and a G5 storm are not different in kind, so much as different in degree and consequence. The same basic physics is present. The scale changes. This is where hard science serves us best. It allows proportion. It allows us to say that geomagnetic storms can be serious without claiming every aurora heralds collapse. It allows us to acknowledge that extreme events are possible without turning uncertainty into fantasy. It allows us to speak of infrastructure risk, radiation exposure, and operational disruption in the same breath as beauty, forecasting, and magnetic elegance. The real system is already rich enough. Exaggeration adds less than precision does. Back in my office, the file has grown heavier, though the room is still quiet. The lamp is steady. The window is dark. But the dark no longer feels empty. It feels populated by structure. I can almost imagine the sun turning in plasma, magnetic flux rising through its surface, active regions tightening like fists that do not yet know when they will unclench. Farther out, I can imagine the corona breathing into the heliosphere, the solar wind carrying fields into a great spiral, a CME expanding through that flow like a weather front made not of water but of magnetized plasma. Closer to home, I can imagine Earth's magnetosphere leaning into the stream, its dayside boundary shifting, its tail stretching, currents threading through geospace, and the upper atmosphere waiting to answer in light. A solar storm, looked at calmly, is not one violent act. It is a long chain of magnetic consequences. The source is deep in the sun's restless structure. The journey passes through a moving heliosphere. The encounter depends on magnetic orientation and planetary response. The visible result may be an aurora over a familiar street, or a graph line sloping in a control room, or a satellite operator making a careful correction, or a radio signal fading where it was expected to hold. Each is a different surface of the same event. And perhaps that is the best place to close tonight's case file. Not with catastrophe, and not with mere spectacle, but with proportion. The sun is not suddenly hostile. It is active in ways stars like ours are active. Earth is not helpless. It has a magnetic shield, an atmosphere, and a scientific community that watches, models, measures, and warns. But neither are we separate from the system. Our satellites, radios, navigation signals, power networks, and even our nighttime skies tell us that plainly. We live under a star, not beside a lamp. When the star grows especially active, the evidence arrives in stages. A flare brightens. Particles race ahead. A cloud of plasma crosses the inner solar system. Earth's magnetic field rearranges itself under strain. Currents grow, radio paths change, satellites feel drag, and the auroral oval swells. Seen all at once, the sequence can feel grand. Seen step by step, it becomes intelligible. And there is comfort in intelligibility. There is comfort in knowing that the strange green arc over a dark field, the sudden alert in a forecast centre, and the old 19th century telegraph report all belong to one connected science. So if the sky ever seems unusually alive, or the forecast quietly mentions geomagnetic activity, or a friend sends you a photo of an aurora from a latitude where it does not usually belong, you will know that the moment did not begin there. It began in a star that rotates differentially, convects, twists its magnetic fields, raises dark sunspots into view, and occasionally lets stored energy go. It crossed a heliosphere already full of flow. It met a planet with a magnetic shield, an atmosphere, and a technological civilization tuned to delicate signals. And for a little while, that whole chain became visible. The office is still quiet now. The page at the edge of the desk has settled. The steam above the mug has thinned away. Outside the window, the sky looks blank again, as if nothing were moving through it. But that is never really true. The sun is still breathing outward. The solar wind is still arriving. Earth's magnetic field is still standing in the flow, yielding a little, holding a little, tracing invisible lines through space that only sometimes write themselves in light. And every so often, the star reminds us, beautifully, electrically, and with great patience, that space has weather too.